All right, here's your circular motion problem. So we got a student. They're on a ride, and they've got a mass of 110 kilograms, and they're spinning on this ride super fast. All right. The ride happens to have a radius of 5 meters and uses a carpeted wall with a coefficient of friction of 0.7 to keep the riders stuck to the sides of the ride without touching the ground when the ride spins. So your goal is to determine the period required to keep the person sliding down the wall. Now, I don't know if you've ever been on one of these rides, but it's pretty cool / nauseating, where it starts you spinning and then you kind of feel like you're pressed against the wall, and that drops the floor out from you, so therefore your feet aren't touching the ground anymore, so you're kind of floating, you're kind of pinned against this wall like kind of like a human fly or something like that. And it just spins really fast, and as long as it's spinning fast enough, then it's good to go. If it doesn't spin fast enough, then you actually slide down the wall. So your job is to figure out what is the period of rotation required to keep the person pinned against the wall. Now, if you do all this correct, then I will tell you the right answer. So pause the video, see what you can see, and I will come back with the answer in a second. All right? So pause it. All right, there's your period. It is 3.75 seconds. So as long as this thing is making one full rotation every 3.75 seconds, then the rider will stay upright and they will not slide down the wall. So how to get that? Well, I'm sure that you did some of the fundamental basic things, like list all your givens, draw a force diagram, and all that fun stuff. So let's see what I did. So here's me listing my givens. All right, my givens are over here. They're over here. They're behind this box. I swear they're behind this box. Any day now, computer, you can do this. There we go. So here's my givens. I knew the mass, I knew the coefficient of friction, I knew the radius. And some of you are like, why do I need the coefficient of friction? Well, that's when drawing a good force diagram comes into play. So if you draw all the forces, you need to remember what's keeping you from sliding down the wall. Well, that's friction. All right. So if I did this, then really you have to remember I've got gravity pulling me down. So something's got to hold me up. And if you're sliding against a wall, that thing holding you up is the not normal force, Szymanski. That's the force of friction. And then you're being pushed towards the center by the wall. So that's your normal force. And all this is then creating that inwards acceleration towards the center of the circle, which is why it's so important when you do your force diagrams. You want to list all your variables, identify where's the center of the circle, what's the direction of acceleration. Now, since you're not sliding down, the force of friction is exactly equal to the force of gravity. So once you have this, you can do net force equations in not just one plane, you can do them in both planes. So you can do them in the x-plane, which is your circular motion plane, so sigma f of c, and you can do them in the y-plane, which if you do it right, you shouldn't have any acceleration whatsoever because you're just stuck there. All right, so do those net force equations in the x-plane, the y-plane, pause the video, come back, see how you did. All right, so there's your y-plane. Did the y-plane, and so if you look in the y-plane, you've got friction is pointing up, so it's positive. Gravity's down, so it's negative. Then I started doing some algebra, so I brought that over here, and then mass is 110. Gravitational field strength is 9.8. Force of friction, I replaced that with mu Fn because I was given mu. And so then I'm trying to solve for Fn because that's what's really making me go in a circle. So that's why I kind of need to go this route. And so I solve for the normal force, and I find it's 1,540 newtons. So once I find Fn, now I can do my net force equation in the x-plane, which is actually my centripetal force, and see how that goes. So when I do that, let's see what I get. Uh-oh. The card game in the classroom's getting hostile. All right, so there we go. Your centripetal force equals mass times centripetal acceleration. Booyah! The only force that's going in the plane of the center of the circle is your normal force, and then you've got your mass. You notice I used 4 pi squared r over t squared for my centripetal acceleration because I was looking for the period, not the speed. So I do all my fun math, sub in everything I know. The only thing I don't know is t. Pardon me. So then all that's left is solving for that period, and you get 3.75 seconds. So hopefully that made sense. Hopefully you'll follow it. And again, follow your golden rules. List your givens, draw a force diagram, net force equation. In this case, net force equations, because we have multiple planes. So never feel like you have to solve it all in one step, because many times these problems take multiple steps. All right. Hope that helped, and I will see you next time.